Our next talk is Richard Wilkinson, who's going to tell us about multi-level and multi-fidelity models.
Okay, thank you very much. So I guess this program is largely about, or in part about, getting the applied mathematicians and the statisticians talking to each other a bit. And everything, the program organisers have been very careful to balance everything. So I guess we've had 2 talks from mathematicians and 1 from Dave, who's a statistician earlier. So you can probably guess I'm a statistician, okay? So I should admit that at the start to set your expectations accordingly. Okay? So I had a very pleasant 4 weeks here in January, okay? And I feel like I learnt a lot. Okay? So I heard so many new ideas from primarily from the mathematicians. It'll take me a couple of years to kind of work through them all to figure out which ones are useful to me and which aren't. But it's kind of very informative and influential on me. Okay? So one of the things I didn't know about before I came really was multi-level or multi-fidelity methods. Okay? So it was one of the topics we talked about quite a bit in January. Anyway, so Peter's twisted my arm a little about giving a talk today, so I'm very grateful for the program invitation, less grateful for this hospital pass of a talk. So normally when I give talks, I'm kind of in a position of being the expert on the subject and talking to people who know less. Today I don't know a great deal about this, but I see there are lots of people in the room who know a great deal about it, so I'm just hoping to get through it without embarrassing myself too much. Okay. So this is what I do now. So the idea in multi-fidelity modelling is we're in a situation where we've got a high fidelity model, okay, that we really care about for some reason. Okay. So I'm going to think about models as functions. Okay. So my high fidelity function maps from some input space x to some output space y. Okay. The kind of thing I have in mind is something like a climate model. Okay. So it might predict the temperature spatially resolved and through time. And a high fidelity model is going to be costly, as in it's going to be computationally expensive to evaluate, okay, and possibly accurate as well. Okay? But the point of difference is to learn about this model. So the situation we find ourselves in multi-fidelity or multi-level modelling is where we've got some other models, these low fidelity models, okay, that are also functions from the same input space x to the same output space y. Okay? And these models are less costly. Yep. We can run them at a fraction of the computational cost. Okay. So here, for example, I've got a regional climate model with a fairly fine grid, okay? And here it's been coarsened to one that's about a third of the resolution. Okay. And presumably, if they're less costly, they're also going to be less accurate. If they're more accurate, we just throw away the high fidelity model and work with that instead. Okay, so we've got a hierarchy of models we're going to think about. Okay. So I'm talking about models on levels 1 to k, okay, all back from the same space to the same output space, okay, where model 1, F1, is going to be my high fidelity model. Okay. And these models may or may not be kind of structurally related to each other. Okay. So in this case here, they are structurally related. It's essentially the same equations, just solved at a different resolution. You discretize the PDEs and solved at differing resolutions. Okay? So I think in applied maths, methods that have that kind of structure are often called multi-level methods. Okay? Or they might not be structurally related in that way. They might just be completely unrelated models that are somehow predicting about the same things. Okay? So for example, in climate, we often have full GCMs, global climate models, okay, that have all sorts in. So they've got atmosphere, ocean, changes in the sun, they've got clouds, they've got plants and all sorts. Okay? Then you might have slightly simple models that might just be ocean models, say, with a very simple box atmosphere attached. So these are often called intermediate complexity models. Okay? Or you might have even simpler models that might just be box models, you know, a box for the ocean that absorbs heat and gives out heat, box for the ocean. Okay? Or even simpler still, there might be kind of phenomenological models that just try and capture something about how the climate behaves through time. Okay? This is the kind of model I like. I kind of about work at that level. Okay? So as I say, the models may or may not be structurally related, and if they are structurally related, this tends to be the kind of methods for analysing that tend to be called multi-level. If they're not, I think that generally falls into the multi-fidelity class. But in each case, they're just predicting from the same input to the same output. Okay. What time am I aiming for, Peter? So I know.
22.
22, okay. So the aim, just to be clear here, is to use this model hierarchy to learn about what the high fidelity predicts. Okay, so we've got some sort of analysis we want to do on the high fidelity model, and we're going to use this entire hierarchy to do that calculation about what the high fidelity model thinks, or would predict in a sense, using this entire hierarchy. Okay? And we're going to try and do it at a lower computational cost, or equivalently, if you like, we're going to learn better for the same cost. We've got a certain computational budget. Let's learn better, which typically means reduce our variance of the things we're estimating. Okay. So what it's not is multi-model, learning from a multi-model ensemble. Okay, we haven't got a collection of information sources, and we're not trying to kind of average the predictions across different models to kind of use the wisdom of the crowd of models. It's not that. It's trying to learn from this high fidelity model. Okay, to this. And learning about this topic, let's talk. There's a really nice paper here, this survey paper about the applied maths approaches by Ben Perestorfer, Wilcox, and Max, who's sat at the back. Okay, and they make this distinction between different type of outer loop applications. Okay, so what they call outer loop applications are things that we would want to repeatedly make calls to the simulator for. Okay. So, for example, we might want to do uncertainty propagation. Okay, so Max this morning talked about estimating statistics of your high-fidelity model. So, for example, I might just want to work out the expected value of the high-fidelity simulator when I've got some random variable x that goes into it and some distribution for x. So that's just uncertainty propagation. I'm uncertain about x, I'm propagating that uncertainty through the model. Okay. Aretha's talk was about inference. Okay. So if we've got some data that we believe relate to the high-fidelity simulator in some way, perhaps some particular input plus an error term, okay, then we might ask, well, what does that data tell us about x? How do we learn a posterior distribution for x given the high-fidelity simulator and the data? Okay. Or optimization, how do we find the optimal value of x? Okay. So one of the differences we've found is that in statistics, generally we have an approach for setting up these kind of problems, and we wouldn't make too much of a distinction between these methods. We've kind of set up our kind of surrogate model approach, and then we do something fairly naive for all of these. In applied maths literature, each of these type of problems is analysed very differently, as I'll point out. Okay. The other nice thing I like about this paper is they talk about this model management strategy. Okay. So this figure is just stolen directly from the paper. Okay. So we've got this outer loop application that's doing one of these three problems, yeah, or something else. The thing we'd like to do is just this outer loop application with this high fidelity model. Okay. So for example, we wanted to estimate this expectation. We could do it by Monte Carlo. We'd pick a random x, work out what the model prediction is for that x, and keep doing it. Okay. So we go round and round this outer loop. A kind of a naive approach would be to find a low fidelity model, okay, that approximates the high fidelity model, and just use that instead. Yeah? So if I've got a really expensive high fidelity model that takes a month to run, but I can build an approximation to it that runs in a few seconds, well, it's pretty good, let's just use that instead. Okay. These multi-fidelity, multi-level methods are about doing a combination of using a combination of these different models. Okay, so we're going to try and use information for all these different fidelity of models to get better estimates of these outer loop applications. Okay, we're going to think about what's the best way of doing that in certain situations. Okay. Okay, so what's the kind of main statistical approach? So, as I say, I'll talk a bit about the difference between statistics and applied maths a bit more towards the end, okay? But we like to needle each other a little bit sometimes. And so I think one of Max's comments, in fact, about statistical approaches is why is it always Gaussian processes? Gaussian processes all the time, okay? And so many of the statistical approaches are based around the ideas of using Gaussian processes. So just out of interest, who here knows about Gaussian processes? Okay, about half, okay. So very brief kind of description. We can think of them as models of functions, probabilistic models of functions. Okay, so we start by setting up some kind of prior specification of what we believe our functions are like. Okay, we've got an input variable x, output variable y here, okay, and our function is a map from x to y, so it's a line on this curve. Oops. Okay, and we start by saying what kind of properties do the lines have? Are they continuous? Are they differentiable? How wiggly are they? How smooth are they? Okay. we then go and collect some data. So in our case, that's doing function calls. Okay, so we evaluate the high fidelity simulator a number of times. So I've evaluated it 3 times here. The points don't really show up, but the evaluation there about 8, evaluation at about 4, is it, and evaluation about 1. Okay, and then we update this picture of our prior specification about these functions, these lines. Okay, we get a posterior specification. Okay. So now we have a model that predicts this relationship between x and y that takes into account the data. Okay, so we have 3 model runs here, and so at the point where we did a model run, so at x equals 1, we know that the value of y was about 0. Okay? So our model now says that. Okay? And similarly at 4 and at 8. Okay? So think of these as kind of probabilistic models of functions. The reason we tend to like them all the time, I'll give various answers to that, okay? But primarily because they're simple to work with, okay? And they have been shown to be have good predictive ability in many cases. Okay? So these are kind of one of the main branch of machine learning regression models. Essentially, they use widely machine learning. So what is a GP? What is a Gaussian process? It's just simply a random process indexed by some variable. Okay, so for any finite set of indices, okay, it has a multivariate Gaussian distribution. So say you know your function at n points. Okay, my Gaussian process prediction model just says that this has a multivariate Gaussian distribution. Okay, and the reason we like Gaussians is because they're mathematically tractable. Okay, so one of the reasons we use them all the time is that they're simple to work with. Okay. They're closed under various operations. So if I've got 2 Gaussian processes and I add them to each other, it's still a Gaussian process. Okay? So I can do things like combine them that way. Okay? More importantly, they're closed under Bayesian conditioning. What does that mean? Okay, it means if I have some observations about this function somewhere, and I say, well, what do I think about this function now I've seen these observations? Okay? Now I've seen these 3 observations, what do I think about the function? It's still just a Gaussian process, and nothing's really changed. I've just updated something in the specification of my model. Okay? So the fact that they're closed in this way is fairly unique to this type of process, okay? And it means that they're easy and mathematically tractable for us to work with. Okay, and also it would be briefly important at the end if I get to it, okay, is that they're closed under any linear operation here. Okay? So if L is a linear operator, for example, differentiation, integration, multiplication by the thing, then applying that linear operator to the Gaussian process gives us another Gaussian process. Okay? So if I model something by Gaussian process, I've automatically modeled its derivatives and its integral and everything else. Okay? I can get that information out for free, essentially. Okay. Another reason they're popular is that they're kind of very flexible and non-parametric tools. So presumably everyone knows about linear regression. Okay. So if you wanted to model the relationship between x and y, okay, one way of doing this is by linear regression, which Max briefly mentioned before. Okay. So we've got a parameter beta that we multiply x by to predict y. Okay. So linear regression is very well understood. We can write down the best possible choice for beta according to some loss function. So if we have a squared loss here, and this is the L2 penalty that Max mentioned. Okay? So if we choose beta to minimize a term like this, okay, we get a simple expression for the best possible value of beta. Okay. So one of the reasons Gaussian processes are useful is that we can replace, well, in general for linear regression, we can replace x here by any feature vector. Okay? So this is a straight line, a linear relationship between y and x. Okay? But I could add an x squared term here to get a quadratic relationship, right? Or a cos term as well. So I get a quadratic relationship with kind of periodic behavior. Okay? Or I could add whatever I like in here. Yeah, I could just keep extending this period vector to get ever more complex functions. For some particular choices of features here, when I should say, I've rewritten this thing here so that the only way that it appears is in terms of inner products. Okay? It doesn't really matter. Okay? But for some sets of features, inner products between features become particularly nice to evaluate. They just become evaluating a kernel function, which is just a function of 2 variables, okay, with a certain property. Okay? So the reason we like Gaussian processes, or one of them, is that for certain tricks, for certain sets of features, we can lift X into an infinite dimensional feature space. Okay, so we can have an infinite number of terms in here. Okay, and if we do that with the right set of infinite number of terms, okay, we find that to evaluate the best value of the parameter, well, that's not quite the right way of thinking, but to make predictions, we never need to evaluate all those features. We just need to evaluate a kernel like this. Okay. So we've gone from modeling in this finite dimensional set of kind of basis vectors, so a constant, linear, quadratic, a cos, okay, to an infinitely rich family, okay, but we've not made the calculation any more difficult. Okay, so this is what is called the kernel trick. Okay, and it's the key behind many kind of machine learning methods like support vector machines and Gaussian processors. Okay, and for any method like this that kind of works by replacing an inner product by a kernel evaluation, you get kind of these nice representative theorems which says all you have to do is work that scales linearly with n, where n is your number of data points. Okay. So why does this matter? Okay. Well, it means that we've gone from living in this linear space, okay, of a small number of features, to this huge, rich, infinite dimensional class of functions. Okay. The jargon is that this RKHS, reproducing kernel Hilbert space. Okay. So just as an example, you could imagine a set of features that is just a set of Gaussian humps everywhere. Okay. I'm going to model any function as a combination of these Gaussian humps. Okay. So maybe if my function is something like this, I want 10 lots of this hump, 10 lots of this hump, 2 lots of this hump, something like this. Okay. As we fill in the number of humps in here, okay, so you can put more and more centers for these humps, these Gaussian kind of curves. Okay, we get a model that tends towards a Gaussian process with a particular choice of covariance function. Okay. So we started off with this finite dimensional thing with lots of terms, okay, but when we get infinite terms, it all of a sudden becomes a lot simpler, and all we're left with is evaluating this kernel function. Okay. So we've got this very rich family. Okay. So what this gives is projects our inference into this RKHS, this reproducing kernel Hilbert space, okay, and it's a richer set of models to work in than if we were just using parametric regression. And in some cases, this RKHS is dense in sets of bounded continuous functions. In other words, we can approximate any bounded continuous function arbitrarily well if we had enough data. Okay, so it's a rich class of family to work with. But the key point is, the amount of work we have to do remains linear in n. Okay, so that's another reason we like Gaussian processes. Okay, let's get that. Okay, so how are these used in multi-fidelity modeling? Okay. So I've already said, what we do. Sorry for jumping about. Okay, we take our simulatory evaluations and we fit a Gaussian process to it, and that's kind of our surrogate model. Okay, we started with these evaluations, we train a Gaussian process, and this is you could think of this as a low-fidelity model if you like. Okay, so in the language of the Perestorfer paper, this is our low-fidelity approximation, our Gaussian process here. That's not normally what we mean by multi-level things in statistics. Here, normally we talk about these co-Kriging approaches. Okay, so first paper to do this was this paper by Peter Craig and Michael and others in '98, and then there's a Mark Kennedy and Tanya Hagen paper in 2000, and there's been lots since, okay, included by Peter and Danny and others here. Okay. So the situation here is we've got this sequence, this hierarchy of models, okay, and we normally refer to these multi-fidelity models as different mechanistic models. So like, this is my high fidelity one, this is my energy balance one, or something like this. Okay. And we're going to model each of them with the Gaussian process, linking the Gaussian processes at these different levels. Okay. So don't worry about that. Okay, we're just going to build a Gaussian process emulator, capital F, of my lower fidelity model, little f. And what we're going to do, we're going to structure this modeling in such a way to borrow strength from level to level. Okay. So this slide's a bit of a mess, okay? But just focus on this bit here, okay? Ignore the rest. So what we do, the assumption is that the highest level model, fk, we can evaluate lots, we can model it really well. Okay? So we start with a Gaussian process model of, that should be an f, sorry, of the highest level, the lowest lowest fidelity model, okay? And then we say at the next fidelity model, the next fidelity layer, okay, we assume that it's some multiple of the previous fidelity model plus another error term, which is also a Gaussian process. Okay? And so the idea is that by structuring the kind of the modeling process in this way, it's called co-Krieging, okay, we end up with a better emulator at the high fidelity level than we would if we just emulated straight away at the high fidelity level. So we've got some runs of a high fidelity model, maybe just a few, okay? And then at the lower fidelity model, we have lots of evaluations. We can get a really good emulator down here, but it doesn't quite match, okay? But by modeling this first, we build a better model up here at this high fidelity thing. Okay, and people have extended that in various ways, which I'm not going to talk about, actually. Okay. So, anyway, one thing just to say is, in machine learning, as you might imagine, they have gone even further with this, okay? So now they have these nested Gaussian process structures. Okay? So we started off with a Gaussian process for each of these f's, and then instead of assuming they are related by kind of just a linear factor, okay, instead they're related by nesting the Gaussian process structure. So G is a Gaussian process and F is a Gaussian process. Okay? And they've become very clever in machine learning at training these what are called deep models. So this is a type of deep Gaussian process here. Okay? And the idea is that by doing this you can get a more flexible family of model again, okay, and get better inference. Okay. So what do these kind of methods normally do? Well, they normally decrease our variance a bit. Okay. So the typical plots I've just nicked from a couple of these papers. I think the one on the right is from this Birdie-Karras paper. Okay, is error of our estimate. So whatever outer loop calculation we're doing, it's estimating an integral in this case. Okay, versus the number of samples of the high fidelity simulator. Okay, and the papers typically show things like, look, you know, if we do this with this co-Krieging approach, this multi-level approach, we get a lower error than if we do it with just a direct Krieging approach. Okay. Okay, so this is typical of the kind of statistical approaches. There's not really any guarantees on performance here. It's just kind of demonstrating it works in a number of examples, okay, and convincing ourselves we're happy it works and that we've made some progress. Okay. So that's going to be a difference from the applied maths approach. The other thing that's different is that typically these kind of things we're working with tens of high fidelity simulator runs here. Many of the applied maths approaches need hundreds or a higher thousands of model runs. Okay? So here the kind of regime of problems we're talking in is a low number of high fidelity runs. Okay? And it's also a type of approach that's suitable for black box models, which isn't always the case either. Okay. So let's talk about the applied maths approaches. Okay, so I really am on dodgy ground now. So what we did in the statistical approach just was we had this outer loop calculation we wanted to do, so an integral. Okay, we trained an emulator, and I just used the emulator to answer it. That's typically what is done there. Okay. Now we're going to think about more sophisticated model management approaches, where we're going to try and use the models at all these different hierarchies. And typically, the approach in mathematics, of course, is on methods which have guarantees. Yeah, one of the things that I've realised from this thing is that a method isn't really accepted as such in numerical analysis unless there are rigorous error bounds and constraints on it. Yep. That's not the case in statistics, because we tend to be working with harder problems quite often. Okay, with like huge climate models, rather than limiting ourselves to equations that we can understand more simply. Okay. So the really nice thing about all these applied math methods is that you get strict guarantees on the errors. Okay, so let's talk about one approach. Again, it's another Max paper on this multi-fidelity uncertainty propagation. Okay. So the basic idea here is really simple. Yeah? Compared to MCMC or anything like that, it's a really straightforward idea. So the idea is we've got some quantity mu that we want to estimate. Okay. And we've got an unbiased estimator, m, of it. Okay. So what does unbiased mean? It means that the expected value of our estimator is a random variable, of course, yeah? Expected value is mu. Okay, so it's unbiased in that sense. And the question is, how can we improve m to get a better estimator? Okay, so this is the idea of control variates. You've probably seen it when you're an undergraduate. Okay? Let's suppose we have some other random variable t, okay, which has some expectation tau. Okay? Then if we form the estimator m star, okay, which is m plus some constant times t minus tau, then that gives us another estimator. Yeah? If m is an estimator, then m star is an estimator, and if m is unbiased, then m star is unbiased. If I take the expectation of m star, I get the expectation of m plus the expectation of t minus tau, which is 0. Okay? So if m is unbiased, m star is unbiased. And that's for any choice of c here. So all this approach does is say, well, let's think about what a good choice of c is. Okay, so it's trivial to show, okay, that the best choice of c is given by this. Doesn't really matter what that is, okay. But it involves the covariance between m and t. Okay? If the covariance between m and t is 0, i.e. they're unrelated, then c is set to 0 and we've not changed anything. Okay? But if there's a relationship between m and t, if they have a non-zero covariance, then we can beat m. Okay? In that case, we get the variance of m star is the variance of m times a number that's less than 1. Okay? So in other words, the variance of this estimator is lower than the variance of m. Okay? Just by adding some multiple of a seemingly unrelated random variable. It is related, it needs a non-zero covariance. Okay? But that's the entire idea behind these multi-fidelity and multi-level approaches. Okay? So the aim is to try and find an estimator t that's highly correlated with m. Okay? If we can find something where the correlation between m and t is high, say 0.9, okay, then we're going to have a big reduction, a factor 100 reduction in the variance. Yep? 1 minus 0.9 squared. No, it's not right, is it? So we're going to have a big reduction in the variance. Okay. 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 So how does multi-fidelity approach work? Well, let's imagine our target, the thing we want to estimate, is the expected value of f1 of x, where f1, if you remember, is our high fidelity simulator. Yep. Well, the obvious thing to do is take a Monte Carlo approximation to it. Okay, we generate a bunch of samples, x, okay, evaluate the high fidelity simulator for each of them, and just work out the Monte Carlo sum. Okay, so I'm going to call that y bar 1m. So 1 to indicate it's formed of samples at the level 1 model, and m to indicate there's m samples. So all we've got to do now is find something that's correlated with this in some way to form a better estimator. Okay? So the idea, I might draw this, is to imagine we've got samples x1 up to xm1, up to xm2, up to xmk, okay, where m1 is less than m2 is less than mk. Okay? And what we do is we evaluate the simulator f2 on the first m2 of these and on the first m1 of them. Okay? So what we've got here is the original estimator we started with, okay, plus a constant times for each of the levels the Monte Carlo estimate using that level simulator at using m2 of the runs and m1 of the runs, okay? Or for the top level with all mk runs and mk minus 1 runs. Okay? And the key thing to note here is that this is kind of trivially going to be an unbiased estimator, okay? Because this is unbiased for S, obviously. Okay? So the way S hat is formed is to take the original estimator, okay, and add something that has expectation 0. Yeah? This is an estimate of the integral for f2 twice, okay, with different terms in it. Okay? But it's going to cancel out, so we get a 0 expectation estimator term here. Okay? So this is also an unbiased estimator. And what they show in the paper is that because these things are highly correlated with the original evaluations, we get a reduction in the variance. Okay. So they set up this optimization problem. They say, well, let's minimize the variance of this estimation. Okay. And the things we can control here are the number of evaluations at each level, M1, M2, and MK. Okay. And these coefficients, alpha, that appear here. Okay. So they set up this optimization problem and solve it. Okay. So, really simple idea, but horribly complicated to do this. I would never have thought this was possible to do by hand, okay? To do it analytically. Anyway, they work out the expressions, okay? And the solution they get for the choices of the alphas and the m's is all a function of the correlation between the lower fidelity models and the high fidelity model, okay? So your answer depends on these things. Okay, so again, they have more theoretical analysis of the things, but the kind of results you get look like this. Okay? So here, what you've got is a plot of your budget, how much computation you can afford to do versus the error. Okay, so you want small error, okay, and the higher the budget, the smaller the error gets. And then they show what the answer would be if you just use the high fidelity model. That's the top line. And then if you use two models, so they use, I think, a Coarsen model and a high fidelity model, okay? And then they use a data fit model, which is like an interpolant, I think, or something like this, okay? And so on. Okay? And it's diminishing returns. By the time they had 6 models in this hierarchy, they're not really improving much. But they've got about 4 orders of magnitude of improvement in this example. Okay? It's a pretty nice example in that they've got really high correlation between the low, the high fidelity model and the next fidelity model, but it's really impressive kind of results. One thing to note here is that there's kind of no assumptions at all on the bounds. Okay, it's just all done by these correlations. Okay, unlike kind of many of the numerical analysis kind of results, there's no need to make assumptions about how the error drops off as the fidelity of the simulator lowers. Okay. Okay, so one of the things we were talking about in the first weeks, with Peter and I in particular, were talking about this, was how can we do this with Gaussian processes? Okay? Can we just take this idea and improve what we do with Gaussian processes to get unbiased estimators? So as a cartoon then, let's imagine I want to integrate this function between 0 and 10, okay, with respect to a uniform density. Okay? The expected value of f of x, where x is a uniform 0, 10 distribution. Okay? So I might start by, oh, it's not shown up, okay, by fitting a Gaussian process around here. That's irritating. Okay? So the red is the original curve. Okay? I've got data points at the crosses, okay? And then I've got a Gaussian process fit, and there's uncertainty. It really hasn't shown up either side of this here, okay? And the uncertainty kind of incorporates this red line. Okay? So it's not a perfect emulator. It doesn't have these wiggles in, but it kind of gets the general trend, right? Okay. So what we do then is evaluate this integral in 3 different ways. Okay, so I've done it just by Monte Carlo with the high fidelity simulator, okay, which is this curve, my high fidelity simulator. I've done it just with the Gaussian process, okay, and then with multi-fidelity Monte Carlo. And I would imagine the budget here is 10. I could do where 1 is 1 high fidelity simulation. Okay. And to get an idea of the sampling variation, I repeated this 1,000 times to get the variation. Okay. So the vertical line here is the truth. And in this case, because it was a really good Gaussian process emulator, the uncertainty kind of looked okay. We get an estimate that's kind of bang on. Okay. The blue line here is what we do if we just use the high fidelity simulator. Okay. And the green line is in between. That's the distribution of the answer we get if we use this multi-fidelity Monte Carlo method. Okay. So in this case, you'd look at this and think, well, why bother with multi-fidelity? Because the Gaussian process works well. But if we do it again, and I use a slightly poorer emulator, we get a different result. Okay? So it's annoying my uncertainty's dropped off, but this is another emulator just trained with 3 points, which is a bit more realistic in high dimensions. So we've kind of got big gaps between our data points. Okay? So the uncertainty doesn't match these wiggles. We now find our Gaussian process estimate that just uses the GP is both confident and wrong. Okay? So there's a bias there. And what the multi-fidelity method has done is to unbias our estimate, essentially. So that's the green estimate here. So we've got an unbiased estimator where the truth lies somewhere in the middle. Okay. Whether unbiasedness is actually useful in practice, you're just going to get 1 point from this curve, is a kind of mute issue. But they've got a method that is unbiased upon replication. Okay. So the problems we found when doing this, then, are that some of the inputs we need to put into these multifidelity methods are things like the variances of the simulators at each level, okay, and the correlation between the simulators at each level. Okay. And of course, if we don't know these quantities, we've got to estimate them. Yeah. And estimating variances and correlations is harder than estimating means, okay, and that's the problem we wanted to start with. Okay. So in a sense, we need some form of estimate of these variances in order to use these multiplicative things. Okay. So one question we kind of think about are how robust are these multi-fidelity methods to poor estimates here? And they look pretty good, I think. Max might be able to answer that in the questions. But it's a question here, you know, what do we do when we don't know these things, and can we estimate them online? What more problematic for using GPs here is that we're going to need 2 or 3 different training sets. Okay? We need a set to train the emulator, a set of high-fidelity model runs to train the emulator, a set of high-fidelity model runs to estimate the correlations and variances, and a set to kind of then form the multi-fidelity Monte Carlo estimator. And we can't reuse them. Okay? The nature, if we're using the Gaussian process anyway, okay? Because the Gaussian process will interpolate the model runs, okay? And so I can't estimate correlations between the high-fidelity simulator on my GP if we're using the same set. Okay? And so somehow we need to kind of estimate these things independently in some way. So one of the things me and Peter were thinking about was, can we do this kind of with a bootstrapping or resampling approach? Is there a way where we can, given a big training set of high fidelity runs, can we kind of repeatedly subsample from them to estimate the variances, train the emulator, and form the multi-fidelity estimator? Okay. I'll skip that. So Aretha said I'd talk about multi-level inference. I didn't quite get that far, so that was my slide for. But there was lots of interest in multi-fidelity inference. Okay. So how long have I got, Peter?
2 minutes.
2 minutes. Okay.
Don't forget each question.
Yeah, no, that's fine. I shall summarise. Okay. So, as I say, I've really enjoyed the time here. Okay, but I've kind of been reminded repeatedly of this kind of 2 cultures lecture. So anyone who lives in the UK and listens to Radio 4 cannot have escaped hearing about this 2 cultures lecture given by C.P. Snow at some point in the 50s. And he's talking about the differences between the humanities people and science people. Okay? And the humanities people are always moaning about the lack of literacy of the scientists. Okay? And the and kind of C.P. Snow kind of says he tries to provoke them by asking, you know, can you do calculus, or can you do what's the second law of thermodynamics? And none of the kind of arts people knew, of course. And he was saying, you know, this is as bad as saying you've never read Shakespeare. Okay? Anyway, it felt a bit like that at times here. So I was trying to think of what the equivalent of these kind of questions are for the statisticians and applied mathematicians. Okay, when we kind of so I guess the applied maths criticism all the time, okay, is where's your theory, where's your error guarantees? And we don't generally have them. Yeah? We don't do things like that. We're just trying to do something better. We're kind of lost in these huge problems, and doing something feels like progress sometimes. Okay, and we convince ourselves we're doing the right things by careful validation and, you know, cross-checking, but we don't have those kind of theoretical guarantees for the models we have. But then our kind of retort might be, well, all your theoretical guarantees are for model land. I think someone used the phrase earlier, yeah? Where, you know, your guarantees guarantee that the approach you're using gives you the exact answer if that model is correct. Okay? And that's kind of the debate we've been having. Okay? There's other differences that typically the mathematical approaches work with, I don't want to say simpler models, but models that they can analyse. Okay? And they put a lot of work into each type of analysis, okay? And you change that a bit, and it's harder. Okay? The statistical approaches are more black box things. We don't ever, well, we don't usually think about the equations, but there's kind of a general approach that works to some extent in a wide range of things. Okay? As I say, I really enjoyed the time here. It's given me enough ideas to borrow from, or steal from the applied mathematicians to keep me going for a very long time. Okay? So thank you for listening.
We've got time for a few questions, Prof.
Richard, thank you for a really nice kind of overview of Gaussian processes for those of us who are in the applied math community. And I guess the question I wanted to ask, and you sort of hinted at this maybe in the final slides, is as an applied mathematician who has spent quite a while trying to implement Gaussian processes and understand the R code, one of the observations we find is they seem to be fairly, not to use easy, but tractable in low dimensions, 1D, 2D. But then when we start trying to calculate our covariance functions or our correlation functions, even for 5, 10, 15, we start getting this explosion of the hyperparameters. And estimating those gets, at least from my perspective, really, really hard The R code seems to be pretty good at, but can you just, are there things that were, places you can point or things you can say about that? Because that's one of the things from an applied math perspective I found was, if you know the covariance functions, this is great, but estimating them was hard.
It is hard, and even in 1D you can get these perverse behaviours.
Thank you.
It's often worse in 1D. So there's various problems. one, they are hard to estimate, and two, there's numerical stability issues in doing so. So generally we cheat, right? We put strong priors on, constrain them. You know, you cross validation. It's not cheating. You know what I mean? It's not an unsupervised process. Okay, it takes a lot of careful. You know, you have to pay attention. It's easy to get it wrong, and in high dimensions, how you spot that is really worrying. And
okay, so thank you. So it's not just me, because that's something that we've looked at, and
no,
it's hard.
No. So you know, you can do GPs up to a certain number of dimensions, but beyond that, you want to reduce your dimension somehow.
What is the progress? One of the things that we've sort of talked would be really nice is taking our theory from differential equations, et cetera, and translating that over so that we get better priors that makes this easier. Is this tractable? Is this another item?
Yeah, so one of the ideas I had early in January, actually, when people talk about these, was thinking about, can we get kind of GPs that obey simple sets of equations? So I actually wrote a grant proposal in January, and we found out yesterday it had been funded for doing exactly this. Okay, so it's not my idea. It's just I spotted a paper that did it, and I thought someone will fund that, and this kind of silly call that came out. So suppose you've got simple linear constraints on a GP, like zero divergence or zero curl, something like that. Okay, it's a very simple idea. If you can write your function as some other operator of another function such that it's automatically satisfied, okay? So if I had to show the example, for the zero divergence, for example, this is your operator f, okay? You want f of your function to be 0 everywhere, okay? If all your functions are of the form, this operator applied to any odd function, it's automatically satisfied. Okay, so this allows us, and because this is a linear operation, okay, this allows us to write down a Gaussian process model, a Gaussian process covariance structure, more importantly, that automatically gives us GPs that have zero divergence, zero curl, or any, in theory at least, we can do it for any fairly simple set of linear operations on things. But yeah, I think that's going to be an interesting idea to go in.
Did you play?
I didn't. I should have, shouldn't I?
So I really liked your last slide in the model line comment, but I was wondering if we could jump back to your two GCM pictures. I mean, I think this issue about uncertainty quantification and uncertainty guidance, where you actually try to move to the real world, is an important one. And so many people think, Jim Berger thinks that uncertainty UQ includes that guidance, and yet in practice it often doesn't, for exactly the reasons you mentioned. But I think there are times where we can do something simpler. So the model on the left, in the north of Italy and the northeast of France, you'll have big flash floods that cause lots of damage and change things. In the model on the right, those just don't happen because the Alps aren't high enough. And so you know before starting that even an infinite number, an unbounded number of runs can't inform that kind of question. And then it's also true that the water that falls out in the model on the left continues on and falls somewhere else. So on long time, climate time scales, you get these feedbacks that, you lose the ability, you know that it can't work. And I'm just curious about your opinion on being able to make it clear that there's a lot of work needs to be gone to get more confidence on when it can work. But there are times when a priori we know that it cannot work. And yet we spend a lot of details presenting our arguments in those cases where we know it can't work. So how do we avoid, is there a moral hazard there for the...
I have no answer. I agree.
Can I answer that?
Yeah.
No, I mean, there's no reason why it wouldn't work. I mean, you do have to do at least one run of the true. So the whole idea is the less accurate models just give you efficiency, but you have to do at least one realization of the truth model. And the truth model then will come and put those things in.
I don't actually. I can actually look at what the real world does, calculate the how to the mountains in my model, and realize that the orographic forcing will not happen.
Where?
Oh, the place I mentioned, the northwest of Italy and the
It
northeast.
doesn't happen in the right model, but it happens in the left model.
So I can tell whether it might happen in this one, that's right. But the talk is about simplifying the model on the left. I agree to show that to have good results, we need to show the model can perform.
So I misunderstood your question.
That's not possible.
So it is trying to do the inference for the model on the left. Okay. I misunderstood. I did.
Okay.
Okay.
No, then I agree.
Yeah. So the question about how you link the two levels, what your general forms are. So my general first comment in the two is that linking them just by having like some rescaling and adding a Gaussian process seems to me a very weak way of actually doing the link. I mean, because when you unwrap it, for example, I mean, you can imagine that you find that there's a regression that fits plus a residual error, which may be a Gaussian process. Then effectively to scale it, effectively is saying it is the same regression, you're just moving parallel. That's a very sort of strong constraint that you do not believe and generally won't happen. Secondly, obviously the more finer model will have more real-world parameters because you've discretized, and its dependence on things like tuning parameters may be decreasing because you have less tuning.
Yeah.
So I think that the work needs to go into that careful description. And I think it's a very rich field, and there's a lot you can do.
So I didn't. I mean, I put it all. I gave a reference to it, but I didn't. I looked at talking about your paper with Jonathan, the coming in Goldstein 2009, where you do make that richer link between the mean functions. I decided it was too intricate for me to put up here. So there are other ways of doing this linking. I agree entirely, and I think that is in practice, I've always thought that's a problem about having different parameters at each level. Here, I guess, the kind of picture that's always in mind is you've got a huge unknown spatial field, like a groundwater flow problem, okay? And it's always like that. Rather than saying you've got these 15 parameters and the next model up it's 27 parameters and so on, I think. I think that's kind of the picture people have in mind when they talk about these things.
Just have a short comment on the last slide. I'm kind of taken aback by this impression that all we do is prove error estimates.
No, I didn't mean like that.
I wouldn't talk about my own background, but I urge you all to look at Ralph's CV and see how many real world problems he's worked on.
I apologize, it was a caricature.
I know.
So some statisticians do maths as well.
But yeah, that was a bit.
Yeah.
Okay, we're running a bit late, but we're going to have a panel session. But while we get the chairs up, I suggest people have 2 minutes to just stretch their legs.